Where is this? Yes, it is here. Yes, so background effect. I just want this. So how can I display my screen fully? If I want to keep my screen over here, then what I can do, I can pin it. How can I pin to screen? Yes, so it is right. Yes, it's here. Okay, let me just fix it. Then we will be starting lecture. Yes, so if it can be done, this applies to no, it's okay. Yes. Okay, so I will be making it a bit smaller so that main content. Yes. So this course, this is the first week of the course, Transport Phenomena of Non-Newtonian Fluids. And in this particular course, we will be actually looking at uh, basics of non-Newtonian fluid and how these fluids are different from the Newtonian fluids. So this is taken by the Professor Nanda Kishore sir, Department of Chemical Engineering, uh, Department of Chemical Engineering, IIT Guwahati. So basic prerequisites of this course is basic fundamental knowledge of fluid mechanics, heat transfer and mass transfer. And if you see that in week one, basics of non-Newtonian fluid have been taught, where sir started with this Newtonian fluids, and then this Newtonian fluids basic have been extended to the various properties of the non-Newtonian fluid, and then different models that are being utilized in order to give the mathematical form to the various physical phenomena which is happening with the non-Newtonian fluids. And then this time-dependent non-Newtonian fluid and viscoelastic non-Newtonian fluid, and then this viscoelastic non-Newtonian fluids, right? So what I'm saying is this first week 4 lecture was entirely about the non-Newtonian fluids, uh, their properties, how they are different, how they behave, various examples of those non-Newtonian fluids, and then this different models that are being used for the non-Newtonian fluids. So there are some fluids which are like which can be fitted to some power law model. Some are maybe fitted to some Carnot model, and then there is Ellis model. So there are different models. Some are time dependent, some are time independent. So like thixotropic, rheopectic, these are time dependent non-Newtonian fluids. And then something called viscoelasticity, where this elastic component inside the fluid give them very different and strange property as compared to the Newtonian fluid. So that have been taught. So how I will be taking the classes, like this is 2 hour session, and we are supposed to ease your learning of weekly classes in terms that it will be a kind of revision session, and then we will be solving around 15 to 20 questions. uh, uh, there will be some numerical problems, and then there will be some objective questions. Mostly these questions are related to the content that has been taught in the first week itself. And then this lecture is will be helping you in solving the weekly assignments. So like till now there is this week 0 assignment and week 1 assignment, and those assignments can be you will feel less struggle while solving those assignments if you go through this particular lecture. So this is a kind of one-to-one session where you are actually interacting with one personnel related to that course, and you are asking your doubts. So this will be a kind of doubt session, as well as this is a kind of revision session, and similar questions will be solved here, which you are about to get in your different weeks, which will be anyway evaluated at the end. So that's it. So in particular in this week we are actually focusing on this four things, which is Newtonian fluids and how the classification of non-Newtonian fluids are done, time independent non-Newtonian fluids, time dependent non-Newtonian fluids, and viscoelastic non-Newtonian fluids, right? So viscoelastic non-Newtonian fluids in some few examples and numerical problem related to that. Okay, so let me just brief you about the contents that were there. So I mean, this screen, if I can increase, okay, yes. So I just want it a bit expanded. Okay, so it is okay. Right now it's okay. Yes. So if you see this, different types of basic properties of non-Newtonian fluids. So before knowing non-Newtonian fluids, I has defined the Newtonian fluids, and then these Newtonian fluids, how these Newtonian fluids are actually. Let me just have my marker over here so that I can write. Just check it. So it is where it is. I'm just fixing the pen tablet. So just give me a second. So let me just fix this. Okay, so it's here. It's right here, right? So we will be using this. Now it's done. Okay, so let's see if so these are some questions that we will be solving, and we just take that to the front slide only. Yes. So these are the questions that we will be solving in today's session. So around, I think it's 4, 5, yes, it's around 23 questions, 22 questions that we will be having look at, and then meanwhile I will be telling you, or it's a revision kind of thing also. So we will be looking at the concepts that has been taught. So sorry, started with the Newtonian fluids, right? So if you see the Newtonian fluids behave in simple searing experiments conducted at behavior in simple searing experiment conducted at given temperature. So if you see, first is through this shear stress versus shear strain curve, if you see that they will be behaving it's like sweet, some glitches are happening. So if you see this. Okay, so it's here. Let me just remove all the juggleries. Yes, yes. So if you see, yes, it is here. Let me just thicken it. If it is thick, it is okay. Yes. I just want to convert it to pen. Let's see now how it will be converted to pen. Yes. So this it's not coming up. Some problem with this. Let me just fix it. Yes, it is now functioning well. Let's just fix it. Yes, it is fixed. Yes. So Newtonian fluid, right? And if you see the, if you remember the shear stress versus shear strain curve, these are our Newtonian fluids, tau versus gamma. So this is when n equals to 1, right? And then anything behaving differently than this particular curve is termed as non-Newtonian fluid, right? Right. dy or something, whatever you mean. So we just see if somebody came. Where is this? Yes. Okay, so it's u by dy, right? So if you see the first question, we will be solving the question, and through the question we will be going towards the concept that are okay. So shear stress versus shear rate curve for Newtonian fluid is linear but not pass through origin. It's non-linear and passes through origin. It's linear and passes through origin. And option D is non-linear but does not pass through origin. So if you see this particular question, it's straightforward, like whatever we discussed in the first slide here. It's, if you see, the solution to this is what? Linear but does not pass through, but no, it passes through, right? So the option C is correct. Option C is correct answer, right? Okay, so if you see this next question, you look at this, and then we will be having a conversation about this. Unit of viscosity of a Newtonian fluid is, right? So you just attempt. So I mean, right now nobody is there. What I feel is so like maybe later these all recordings are these all videos are being recorded, and later you can watch it at your will, and definitely it is going to help you in solving your weekly assignments, and at the same time in revising whatever steps you got to know uh, this during this particular week, right? So if this is, you see, tau equals to mu vu by by, right? And this tau is what, force per unit over here, right? Force per unit area equals to mu du by dy. It's u by y, right? You can write it, or else what you can do is, actually I am just going to give them some units. So u is meter per second, and it's meter, and then force, you know, ma means kg, meter per second square, and then this is what, area, meter square, right? And then if you see mu equals to what, kg meter per second square, meter square into meter into second meter. So what you are going to do, kg per second meter, right? And then if you see Pascal is pressure. Pressure means force upon area, right? And this here stress is what? This was pressure. No, shear stress is what? So if you see this exactly, the answer is this Pascal second. Pascal second you will get this Pascal. Pascal is pressure. So force per unit area into second is kg second into square, right? So that's the one thing that you are going to get, right? So it will come as once you solve it. So you can attempt it like this, right? So another unit of viscosity is this centipoise, poise, and this what I'm saying is centipoise, poise, and this sometimes Stokes also. People go for Stokes also, right? So that's the thing that has to be taken into consideration. Okay, so so if you see the kg per meter second, it will be converted into Pascal second, right? So that is the main solution that you will get out of this. So if you actually see in so let's see what we got, right? So that is the first question that we were solving. Okay. Okay. So let's. I can give you detailed solution for that. So this positive calculations are here. Whatever I have solved, the same I am just giving you in this particular form. Just keep it here, and then as the similar calculations are over here, right? So this is the calculation solution for the same what we have just solved. Okay. So now the next question is, which is third question, is this one. So this is basic fluid mechanics question. It is, I think, not told by sir in this particular lecture, but just you attempt and then I will be helping you. Critical Reynolds number for the transition from laminar to turbulent flow of a Newtonian fluid in pipe, right? Just attempt. So you can just attempt about this order of magnitude also. So like around what this value come. Okay. Then we will be discussing this particular question. So that will help you. So this critical Reynolds number for the transition from this. So what I'm saying is there is this pipe. Okay. And through this pipe there is flow. V, velocity, the density of the fluid rho, viscosity is mu. Okay. And this fluid is going through this pipe. So you know that there will be formation, parabolic velocity profile formation. Okay. And this velocity profile, which is here, it will be maximum at the center and then gradually it is decreasing, right? So for this particular system, what is the critical Reynolds number before which you say that the flow is laminar? Okay. Laminar, then transient, then turbulent, right? Okay. So if you remember the discussions in your basic fluid mechanics courses, what you know is this this 2300, which is 2300, right? So I will be just telling you this this basic fluid mechanics concept, that for the pipe flow, right, for this pipe flow, if you see this, right, this the critical Reynolds number for the transition from the laminar to turbulent flow is in a Newtonian fluid inside a pipe is this 2300, right? So if you see this 2300, this value comes from this stability analysis. Okay, how this value is coming from? there is something called linear stability analysis. Linear stability analysis, where you actually perturb the system. I mean that there is this fully developed velocity profile within the pipe flow, right? And then in that, this fully developed velocity profile is perturbed. There are different type of perturbation: sinusoidal, cosine, exponential, in the form of normal mode. And then you look for this. What are the critical factors they are leading to system from stability to non-stability, which is instability, right? So this before 2000 they say that it's laminar, smooth, orderly layer. After 4000 they say that it's turbulent, chaotic, and mixed. So between this is the transition. Okay, so this is like something 2000, not 2000, 2300, then 4000. Above 4000 is the turbulent, below that is laminar, and in between is the transient, right? So the order of magnitude for that is this C option, which is around 1000, that says, and C option is correct answer, right? So I will be just piecing up a bit. In between we will be going to the slides also when the questions will be coming around those topics. So till now, like basic fluid mechanics stuffs are coming up because this is zero assignment practice. Then we will be going for week 1 assignment. So zero assignment is something which is given to you before the commencement of the first week, just to brush up your basic concept related to the course content, right? So now another one is this friction factor, right? Yes, this is friction factor related question. So you just read this question and then you just read this question, and then we will be actually looking at the answer for this question, right? So friction factor, what is that, and how they are defined? Okay, so if you remember, then you will get it right. Friction factor for the laminar flow of a Newtonian fluid flowing through a pipe is, right? Just attempt this. Okay, so you just attempt it, then we will be going for the solution, right? So through the pipe only, again flow is happening. So this is the pipe, and then fluid flow is happening. Okay, and then there are different options related. This is Reynolds number. Reynolds number, you know, if the diameter is d, then density of the fluid is rho, viscosity is smooth, then rho v d. V is the velocity, right? So the friction factor F for a laminar flow, let me just see if I am online. Right? Yes, I am online. And things are live mode. Yes. Okay. Okay. Now, yes. So in laminar flow of a non-Newtonian Newtonian fluid is in a circular pipe is given by this what you say 16 by R, you know. There are two types of this definitions that I will be going through. So one is this F equals to this 64 divided by R. What is that? If you see, this is this Darcy-Weisbach friction factor. Okay, Darcy-Weisbach. fixer factor, right? Right. And so so there is 4 times of finding fixer factor is the Darcy fixer factor. So we can say F Darcy equals to 4 times of F finding. So this is the finding fixer factor that we are having option here. Option B. Option B is correct. That is F fanning equals to 16 divided by 1 R, right? So that is the one thing that okay, right. This was the basic. So this also you can keep detailed of this, right? So I can just keep it in this slide so that later if you go through you understanding this. Right now the next question is very basic question. As this question is transport phenomena, so it will be involving everything from fluid mechanics, heat transfer and mass transfer. So this is kind of revision for all of those things that could be somewhere down the line coming to the discussion in this particular. So very famous Fourier law of heat transfer, heat conduction. So this Q equals to minus K dt by dy, right? And then Q dt by dy equals to minus K. So there are different options, so you just have to attempt which one is correct, right? So you just attempt it, then we will be discussing it, right? So if you see what I'm saying is these are let me just come to the line. Okay, so if you see this, what I'm saying is this entire discussion of transport phenomena. In transport phenomena, what is transport phenomena at first? This is transfer of something from one particular point to another particular point. So this transfer could happen in many ways. One is this fluid transfer, where the fluid mechanical concepts will be used, right? Another one is this transport of heat, and then transport of mass, right? One gas is diffusing from one, like for example perfume. So whenever you put the perfume, then entire room smells out, right? What happens? The point where this perfume is coming out of the nozzle, there the concentration of the perfume molecules are very high as compared to the surrounding. So there is this diffusion, molecular diffusion happening, and with the time this molecular diffusion diffuses around, takes the entire volume wherever the perfume has been sprayed, and then this mass transfer is happening. Again this perfume molecules are a kind of fluid. So the fluid dynamic concepts are very important in order to understand this. And then the heat transfer. So this transport phenomena actually deals with all these things together, right? Means everything is under same umbrella, where you are looking at a problem which is involving all these transport phenomena, which is heat transfer, mass transfer and fluid mechanics, and many times different fields like electrical field, magnetic field, optics, everything coming together within one single problem. And you are actually looking at the problem through multi-dimensional aspects. So that's the main thing why uh, people started looking at systems not separately, like only heat transfer, mass transfer, fluid mechanics, rather together. Because when you look at together, then you will actually see dependencies between different parameters which are part of fluid mechanics or part of mass transfer or part of heat transfer, right? So that's why this particular course is and here another level of complexity is that we are dealing with a non-Newtonian fluid. So this the non-Newtonian fluids, most of the fluids, rather all the fluids that we are dealing with in regular, except few, are non-Newtonian. So the knowledge about them is very necessary in order to facilitate the research in this particular area, right? So now coming to the point, if you see this Fourier law, okay, so what is that? If you know the basic basic definitions by which this Fourier law starts, is this this heat, the rate of heat transfer is directly proportional to the gradient of temperature, right? And then that proportionality constant, when gets omitted, then there is this equals sign is omitted, proportional constant omitted, then there is some constant coming up which is called the thermal conductivity, right? So the rate of heat transfer through a material which is solid, okay, or anything through a material is proportional to the gradient, or some says negative gradient of the temperature, and it is also proportional to the area through the through which heat is flowing, right? So in mathematical form, if you look at, then it's q dt by dy or dx, whatever, right? So in words, if you see, heat flows in the direction of decreasing temperature. That's why that negative sign is coming up. And then the amount of heat conducted is proportional to the temperature gradient of the and the thermal conductivity. So that's what we were looking at. And if you see this in very lucid manner, then you will actually realize that these are very important concepts in terms, if you actually want to pursue research uh, in fluid or heat transfer or overall transfer, any research work which is being done, there is a big need of learning all these transport phenomena together, right? So this is the the main thing. Let me just put it here, so that this solution remains with you. So let me just put it on next slide, because so that's what this. So the which option is correct? Let us see. Option A is correct, right? K dt by dt, right? Option A is correct. Okay, so we will be now solving rapidly. Okay, so if you see this next question, thermal conductivity of the material has unit. So if you remember the unit of thermal conductivity, then through the upper equation you can actually see. Okay. The equation that we have just solved, the Fourier equation, through that only you can derive it. So so this, if you see what per meter K, right? So That's the one thing that we will be getting. So let us see. It's what? Q equals to minus k dt by dy or dx, right? And if you see, this k is what? Minus q divided by dt by dx, right? And here if you see, this is what? Watt per meter square, which is q, divided by kx, k per meter. So it's Kelvin per unit, right? And if you solve it, you will be getting what I'm saying is kg meter per second. So through that, if you solve, you will be actually getting this watt per time k. And here, if you see, this is d of, and here, if you see this 1 watt equals to what? 1 joule per second, the rate of heat transfer or something, energy transfer, right? Kg meter square per. So this was the one thing that is using. Okay. So that's it for this particular question. Now moving to the next question. If you see, let us see Prandtl number for the fluid, Newtonian fluid is defined as what? What is Prandtl number? Prandtl number. What is Prandtl number? So the Prandtl number, if you see, it comes in heat transfer, and especially it comes when there is this it's this it is a dimensionless number first of all, and then it relates the momentum diffusivity to the thermal diffusivity, right? So it describes how fast the momentum diffuses. So momentum diffusivity to the thermal diffusivity. So how fast momentum diffuses compared to the heat in fluid, right? So now if you see basics about that, so if this Prandtl number is defined in that way, so if you see momentum diffusivity to thermal diffusivity, right? So if you see this Prandtl number is what? Momentum diffusivity to momentum diffusivity to thermal diffusivity, right? Any diffusivity is having unit of what? Meter square per second, right? So that is one thing. That one question we just solved. I think I will really solve it. So this meter square per second will be the correct answer for any diffusivity, thermal, mass, and water. So that is one thing that you can relate to. Just let me solve the previous question then. So if you see this is defined as this momentum diffusivity is measure of what? Kinematic viscosity to thermal diffusivity, which is alpha, right? So this is mu by rho divided by alpha is what? K upon rho Cp. In heat transfer process, if you remember, and then this comes out to be Cp mu divided by K, right? So if this Prandtl number is low, it means what? The thermal diffusivity dominates. It means what? Heat spreads faster than the momentum, right? And if this Prandtl number is high, what? Momentum spreads faster than the heat. Okay, so let's keep it here. This particular discussion that we just discussed, let's keep it there so that you actually have entire thing in your head when you revise it, right? So let me just keep it here. No titles, nothing, just okay. So this is So if you see, keep it here, right? So that's what. And then if it is Prandtl number is 1, then what is there? This air, water, and moderate temperature they are having. Sometimes oils are having high Prandtl number, and then low Prandtl number is with liquid metals, right? So now the next question that we were talking about was alpha. Alpha was what? Rho by mu Cp, right? K by mu Cp. I think that's this K by rho Cp, right? If you see, this is K by rho Cp, K upon rho Cp, right? Or alpha is what? This is thermal, and if it is momentum, then it will be mu by rho, right? Mu by rho. And if it is other one, then it is dAV by what? dAV by what? Remember? dAV by what? No dAV by mu, right? You have to just see that. Okay. So that is important. If you see that, so this mu d mu by rho d, right? Right there. It's what? It's what? It's what? If you see, it's mu by rho d. Okay. So momentum diffusivity to mass diffusivity. Momentum to mass. Okay. So mass diffusivity, right? So this is nothing but DAB, diffusivity, no, right? It's only DAB. Here I thought it's the schemate number. No, here we don't have to write this. So just diffusivity is different diffusivities we are talking about, right? DAB, right? So the unit to this is what? If you remember this and this, you will see that the unit comes out to meters per second. Okay. So we will be like, if you see, this is Pascal second user, and this is kg per meter cube. Then the Pascal second euro. Then this is kg per meter second, and then this is what? Kg per meter cube, right? So then kg cancel, and then meter it comes out to be meter square per second, right? So we will get this meter square per second as the price. So option B is correct answer, right? So we are with good pace, around 50 minutes, and we have solved like 0th assignment related stuffs. So this is that we have just solved. So let us see. This is a schematic number. So about that we were talking. So I thought this question only. So schematic number, if you see that this is defined as what? Schematic number is defined as what? Let us have different color. It is defined as mu by d. Momentum diffusivity, the mass diffusivity. It is what? Mu by rho, and this is d. Sometimes people call it DAB, the mu by rho, right? And now, if you see, this is what this is. This is momentum diffusivity, right? To what? Mass diffusivity, right? So momentum diffusivity to mass diffusivity. Okay, so if things are going well, then like so now just think of if this schematic number value is very low, then what will happen? Then what will happen? Either the momentum diffusivity is very low or the mass diffusivity is very high. So in any case, this momentum diffusivity is lower than the mass diffusivity, means mass diffuses faster than momentum, like gases. So for gases, what will be going to happen? Schematic number is low, and it is very simple to visualize any dimensionless number looking at the materials around us, if it is gases or liquid or anything, right? If this schematic number is high, it means, and reverse is true, means momentum diffusivity is higher than mass, so momentum diffuses faster than oil. Like oil faster than mass means oil or viscous liquids, in those you see momentum diffuses faster, right? So that feeling is important. So it's not like the mass or something. In fluid mechanics, you may have gone through this continuity equation, Bernoulli equation, Navier-Stokes equation, and then in heat transfer thermal equation, different mass transfer, this Fick's law, and then diffusion equation coming from the energy balance, mass balance, and momentum balance, right? So those things are important, but everything is defining some physical phenomena, and that physical phenomena has to be actually thought of before actually looking at different stuffs, right? So that's it for this particular question. Some detail about this question I will be adding up here just to make sure that everything stays with you. So these all are very important concepts, right? And if you, so for what kind of liquids you can expect that this schematic number is around 1. So schematic number is high, low, you understand. If it is high, then you got to know that it is oil or something. If it is low, then if it is 1, then what you will call that? What you are going to say if it is 1? So it is 1 for very light liquids, in between those. It's not gas, it's not liquid. Okay, light liquids, right? These are light liquids. So moving to the next question is this: what is Fick's law? So till now you saw that it is for the mass transfer, very basic law that governs the transport of mass, right? So this is the one. So in the mass transfer, you may have gone through various subjects, including this. I mean, this diffusion, starting from diffusion, then absorption, then this distillation, then this extraction, adsorption, and then people call that leaching, and then in chemical reaction engineering also through catalyst surface, lots of mass transport phenomena are happening. So entire chemical engineering, if you see the applications which are there in the chemical reaction engineering in CRE and this mass transfer 1 and 2 everywhere, if you see, these are not only transport of one thing, this is so transport of combined things, where in the CRE you see non-isothermal reactors, those things. So it's like everything is there: heat transfer, mass transfer, momentum transfer, right? But in between, everything is controlled by this transport phenomena. Okay, so this transport phenomena, if you see, it is combination of heat, mass, and momentum. Then the condition at which this is happening, that also plays a very vital role for actually determining the behavior at that, and that is the part of thermodynamics. So this if you see this in chemical engineering there is this classical thermodynamics part, and then this another one is what uh, another one is this chemical thermodynamic part. So the chemical thermodynamic part actually involves more of the species part, this mass transfer part, the chemical potential, fugacity of multi-component system, and then this how the chemical potential gives free energy for the mixer. Those things are calculated, enthalpy, entropy, right? So those are the things which are important in order to define the state of the system, right? And for given state, at a given state, at a given condition, if some phenomena is happening, that is actually explained through this combination of heat, mass, and momentum coming up together in the kind of transport phenomena, right? So this fixed law, if you see and if you remember the mass transfers, there you have been taught that this fixed law, this J, which is sometimes J or Ca, it is defined as Einstein diffusivity dc by dt. It is similar to the one where this temperature was there and here thermal conductivity was there. Okay, Fourier's law, right? So here there are two laws of fixed. So one is for the steady state and for one another one is for non-steady state. So this one is for steady state. If you see, another one I will be just telling you in a minute, but just look at the basic that what this defines. So this actually describes how particles or atoms or molecules or any ion diffuses. That is, they move from a region of high concentration to the region of low concentration, right? So if you see how they are actually going from a region of higher concentration to the region of lower concentration, then you are going to actually appreciate what is actually happening in various systems around, right? Okay, so that is the fixed law. Okay, so now if let me just explain. So diffusivity unit, you know that it's meter square per second, right? And this is d c by dt. So higher concentration to lower concentration, that's why towards lower concentration. So final minus initial gets the negative value of dc by dx, right? So the negative sign indicates what? The diffusion from high to low, right? And then if you see there is another law which is the second law of heat transfer, and so the second law of this second fixed law for the diffuser. And there if you see this how concentration changes with time, that is also defined, right? So that is unsteady first of all, right? That is for unsteady. Okay, and if you remember that it is just right, this was not there, just for your information if it comes final exam. So fixed second law, it is non-steady state diffusion where this concentration is actually varying both spatially as well as temporal variations there. So it is a transient problem, right? And then it describes how concentration changes with time due to diffusion, right? And then let's see if you remember. So how the concentration changes due to diffusion, and then how this actually governs the phenomena, right? Yes, it is not. Okay, and then applies with the concentration variation with both position and time, right? Okay, so that's it. The first part is completed now, which was the week 0. Now we are moving towards some difficult step that I will be solving. Let me just see if things are working fine. So if yes, it's okay. So you see that things started with this, I mean this Newtonian, and then this different Newtonian fluids at the room temperature, starting from this, if you see this air, benzene, so it's not the viscosity which actually says that a fluid is Newtonian or non-Newtonian. It's the shear stress versus shear stress versus strain rate behavior. So how they are depending on each other is the actual thing that has to be looked at while determining where the fluid is behaving, and in that also what fits to what particular well-defined models we have discussed. So non-Newtonian fluid is they are deviating from the Newtonian first. So their rheogram may be shear stress versus shear rate. We call that rheogram. They are this non-linear, and they do not pass through the origin, right? And then apparent viscosity, which is local shear stress divided by its shear rate. So here it's not like if it is linear like Newtonian, right? So you can define it locally. For example, if it is Newtonian and it is linearly depending on the things, then you can define it. Okay, but in this case it's non-linear. So if it is non-linear, so viscosity will be changing locally. If you see a slope, right? So slope is changing locally. In the viscosity is instantly at different shear rates are different, right? So local shear stress divided by the shear rate is defined as the apparent viscosity, which is the main thing that has to be looked at for the non-Newtonian fluid. So not constant, it is not constant for a given temperature and pressure, right? And it depends on the fluid conditions such as the geometry, shear rate, etc., and also depends on the kinematic history of the fluid under consideration. So the kinematic history, those things have been taught. You may have seen in the non-Newtonian time independent non-Newtonian fluids also, and also this viscoelastic fluids and this time dependent one. So the history is another thing that has to be looked at. Okay, so these are some examples that has been taught to you. You look at and then feel this around you in like chocolates, cool slurries, sewage slush, wet bench sands, crude oils, etc. Right? So these are some ranges of viscosity that has been given to you. So it's not like very high viscosity means non-Newtonian or something. So classification was the time independent non-Newtonian fluids, time dependent non-Newtonian fluid, viscoelastic fluid. Entire this week, the next 3 lectures were around this only. For the second lecture, third lecture, and fourth lecture, right? So that's what it for the first week, if you remember. So I will be meanwhile taking you through different lectures, what sir has taught and what has to be kept under focus, what are the important points. So if you see this another lecture starts with the classification, and here what I was saying is this this is the linear Newtonian thing, and then non-linear curves are there. So there is another thing that is here, you see Bingham plastic, where it is similar to the Newtonian one, it is linear, but this linearity is not showing zero shear stress at zero shear rate, right? So that's why it comes under the non-Newtonian fluid, right? So this viscoplastic fluids, shear thinning or pseudoplastic fluids, shear thinning, this one, and then this one, which is dilatant shear thickening fluids, viscosity is grating, so you can see the slopes, and then this gamma star yx equals to the direction of shear is function of tau yx or vice versa, right? So if you see that shear thinning fluids, these are measure fluid which are deviating from the Newtonian behavior, majority of the behavior from the Newtonian behavior, and they are having shear thinning behavior. Okay, so their apparent viscosity decreases with increase in this viscosity in shear rate, right? So this is temporary viscosity loss or pseudoplastic material. At very low and high shear rate, these shear stress increases proportional with the shear rate, and then this, so intermediate is also there. So these are some examples for the given example. Okay, so you see that, so at very low or very high there is this deviation, and then in between there is different value. So this is different arrangement in this viscometer, and then accordingly it has been measured. So these are some example of shear thinning fluid which is pseudoplastic, some examples of shear thickening fluids. So these are some models for shear thinning fluids. So Ostwald de Walle model, which is power law model. So we will be solving some questions around it. Then their examples. Then Carew viscous model, viscosity model. It is mostly sometimes good for the biological things also, where the network kind of stuffs are there. And then another one was this Ellis model. You see Ellis fluid model. So we will be looking at that also. And then viscoplastic fluid behavior, which is this some threshold tau naught, which is here 17 Pascal. It's not zero at zero shear rate, right? So different mathematical models are used for the viscoplastic materials, shear thickening, shear thinning materials, and then time dependent material, and at the end viscoelastic materials. Okay, so for shear thickening, you see this shear thickening of titanium oxide fluids, how the shear stress versus shear rate curve is changing. So you see at this particular concentration, which is 12, it's showing very linear behavior, right? Not like Newtonian, but yes, it is linear. But you see for the higher concentration, which is 47, how much deviation is there. So that has to be actually looked at. So this was first two lecture. It was a kind of brief to things that was there, and then let's solve some more questions on the topics that we just discussed. So if you see this, we are having very less time. Oh no, we can easily solve. We are having 10 or 12 questions only, so it's still 1 hour. Okay, so we'll be slowly making our pace, solving the questions, and then clubbing up the things together, right? So the shearing viscosity of the fluid in 1 m millipascal second. So what is the viscosity if it undergoes unidirectional elongation, deformation? Okay, so if you remember the starting of the lecture, right? So what I'm saying is, let me just take you to that particular concept. If you remember, yes, it's here. We are going towards that. This one. So viscosity of the same non-Newtonian fluid under different type of deformation are in simple proportional to one another. Okay, so if you are looking at unidirectional fluid, right, or this unidirectional flow, bidirectional flow, or this tridirectional flow, right? Then this, if you remember that it actually takes care of what I'm saying is this viscosity of same Newtonian fluid under different type of deformation are in simple groups. So this is for unidirectional, this is for bidirectional, this is for planar. Okay, so 9 component is there for planar, and then this. So if it is this isotropic viscosity, right, then you can see that for unidirectional it is mu e by mu equals to 3, right? So what I'm saying is, if mu e by mu, where is this? Cursor is not coming here. No, it is not coming here. Let me see if things are fine. No, it is not. Yes. No, it's here. Okay, so this got changed. Sorry. Now it should. Yes. So this mu e for unidirectional elongation, right? Divided by mu, which is this viscosity, equals to 3 for unidirectional. Then mu e will be what? 3 into mu. 3 into mu is what? 1 MPas. It will get 3 MPas, right? So B option is correct answer. B is correct answer, right? This is B option is correct answer. And if you see this this particular thing, yes, it is here. So the next question is, if you see, we are solving it. Yes, water at room temperature has shear viscosity of 1 m Pascal second. Okay, shearing viscosity. So shearing viscosity is what? Mu is what? 1 millipascal, right? At a shear rate of what? Shear rate is what? What? 10 seconds, right? What would be the viscosity at this half shear rate? Okay, so what will be the viscosity at this half shear rate? Okay, so what will be the viscosity at this half shear stress? So these videos are recorded, so later also you can watch it at your pace. And then another thing is, if you feel any queries, you can also post your doubts on the discussion forum, that will be addressed. And also you can keep your doubt with you. We will discuss in the next class. So every week, Saturday, 7 to 9, I will be taking weekly classes. So I will be solving mostly the assignments related to the question that will help you to solve the assignment. And definitely these things, whatever I am teaching, and then whatever will be coming every week through the assignment to you, those combining them together will make some probable questions that can be asked in the final exam. So that will anyway help attending these classes, right? So this is one thing. And yes, so water, so if you see for the water, if you see, it is a Newtonian fluid, if you remember. So for this shear stress versus shear rate, this will be linear, right? And for this, the viscosity is given as mu is what? Slow, right? It is given as 1 yes. Okay. So this is common sense problem, rather. So if you see that it's 1 already, right? And even you change the shear rate, the slope will be everywhere 1. Water is Newtonian, right? Standard example. So option A is correct answer. right? So we will solve all the tough questions now, all the questions together, and then at the end we will be solving very slowly. There is 2 or 3 questions, bigger questions that will take some time, but anyway we will complete it. These two are related questions, and then this is another one that will be related to Deborah number, and then these are some. So no problem. We are this. Okay. So this is here. Then our equation. Let's make it big. Whether this visible? Yes. Okay, and let's. It's what? It should be ABC, right? Let's make it ABC. No problem. So under what condition the power law model, which is tau ix equals to m gamma yx to the power n of a time independent non-Newtonian fluid reduces to the Newtonian behavior. So if you see for Newtonian, what was the answer? This tau ix equals to what? Viscosity times. So how they are going to there? So if you see tau yx equals to m gamma dot yx to the power n, and if this m equals to mu and m equals to 1, then it will be going right. So this m equals to 1 is correct. C is correct answer. Okay, so you see this. C is correct answer, right? So next question is under what condition cross viscosity model, which is this in front of you, is reducing to power law model, right? So just think about this, how this cross viscosity model will be reduced to power law model. So if you remember this particular thing, if we see how it is going to meet that particular model. So this was their second lecture where the models were there, and we just saw that. So let us look at it. Okay. So these were different models that has been taught to you. Okay. So there is one question related. This is cross viscosity model, right? So here the apparent viscosity by this model is given at this mu minus mu infinite divided by mu 0 minus this equals to this 1 upon 1 plus k gamma dot yx, okay, gamma dot yx, right? So so this here, if you say how it is going to reduce to the power law, if here it says you can also see this here, if you write it in terms of this mu 0 minus mu divided by mu minus mu infinity. Okay, in this case if you put this k to the 0, okay, then this model will reduce to the Newtonian, right? So mu apparent is nothing but viscosity, right? So mu will be cancelling and mu 0 will be mu infinite, means everywhere the viscosity is same. And for mu is when mu is very small than mu 0, okay, then numerator will be mu 0 in this particular one, and then mu is greater than mu infinite. then so it will come mu 0 by mu. Okay, so this mu 0 by mu, and then here it will reduce to the power 1, right? For very, when your viscosity is very lower than 0 shear viscosity, and when your viscosity is very high as compared to infinite shear viscosity, right? Then you are going to see these things. Okay, so what I'm saying is, for this one, the viscosity is very lower than this, very high. So this both A and B is correct. So it is single choice, then C option is correct. Otherwise, A, B, C is correct, right? If you see this one, now this was what? When you solve it, it will come out mu 0 minus mu apparent divided by mu apparent minus mu infinite. Okay, this will be equals to k dot gamma by x to the power n. Okay, and this is n dash. It's not same as n. Like that. This is some other n. So here, if you see, then you will get C is correct. So this was taught. So maybe I will put that particular slides screenshot over there, just to keep you reminded of the concept. So like I have been told to give you PDF also, that whatever we are discussing, right? So that PDF we can make. So anyway, this is part of the same course, so we can use those slides and then learn the concepts in a very effective and easy manner, so that within one class we can actually address entire 4V, because on an average half an hour plus minus 10 minute BC we get for each classes, right? So this is another question that is related to Ellis model. Okay. Yes. So in Ellis model, fluid model, which is this one, what tau half indicates, if you see, it is very clearly explained in the class. Okay, so this, if you remember, the one that is here is shear stress related things, and one of the main important thing about this is option A is shear stress value at which apparent viscosity increases to double of the mu infinite. Shear stress value at which apparent viscosity increases to the double of the mu 0 value. So at which the drops to the half of mu infinite, half of mu. So if you remember the discussion, let me just take you again to the slide. This was the Ellis model that was taught to you, and let us just take the things for reference. The question over there. Okay, so this one, if you see, it's a bit slow, but so this tau half value of the shear stress at which apparent viscosity has dropped to half of the half at is 0 shear viscosity. Okay, so this is clearly mentioned in the class, right? That's it, right? So this one is what? Double, no, half of it. This D option is correct, right? Is correct. Okay. So that's the one thing. So you can also refer to the slides, the course material that is being provided to you. So this just quick revision about this. When the power law, deviation from the power law is significant only at low shear rate, then it is more appropriate. So this model, and here the apparent viscosity is giving at mu0 divided by 1 plus tau ix divided by tau half to the power alpha minus 1. Here alpha is the measure of shear thinning, right? So if you see this, it is the same as n in the power law, okay? But here it is greater than 1, okay? So once it is greater than 1, if you see, then it is for what? For shear thinning, right? So greater the value of alpha, greater is the extent of the shear thinning value. So on this also you can get some questions in the final exams. Okay, so the next question is in the Ellis model, which is mu0 divided by the one that we have looked at. Just let me just make it a bit big so that it's reachable to do. So let me just see if things are going well. Yes. So this Alice model, you see different models for for shear thinning, shear thickening, viscoelastic, that will be coming time dependent, those things. So if you see, these are different options that you are having. This is option A, option B, option C, option D. Let me just put A, B, C, D. It is not here. How can I take it somewhere? Yes. Let's take it. No, it will not come. Okay, so we can insert ABC. No issues. Okay. So it's A. One is A, one is B, one is C, and one is D. Okay, so it's done, right? So then, when it reduces to the power law model, then this is greater than 1. If you remember, right? Then what is the equation for M? Okay, of power law equation in the terms of Alice. So we can derive it, right? So if you wish to derive it, let's come here, and if you see that this Alice model, when it reduces to power law, then the value of M is this one. And how you are going to get it to the power law? The denominator second term, which is this 1 plus tau I divided by tau half to the power alpha minus 1, that term is very high. So when it is very high, then you can actually omit that. Okay. So it reduces to power law model with M equals to this, which is mu0 and alpha is what? Alpha is what? N equals to 1 by alpha. So that is the important thing, right? So from here you see mu0 tau half to the power alpha minus 1, right? Alpha divided by 1 by alpha. So if this 1 by alpha is there or not, let's see. 1 by alpha is there, right? So your option A is correct answer, what I feel. Okay. Option A is correct. Okay, so let's keep it with you. So these slides will come because once sometimes at the end to revise your stuffs. And then to revise your things. you need these slides for the quick revision purpose, right? And if it is with you, yes, you just here somewhere, I think after this it is right. So now if you see the next question, so let's keep it, we will be solving it at the end. Just solve the remaining some theoretical question first. For time dependent, we will take time for that question. Okay, so at the end we will take time, some extra time also to solve that. So for time dependent non-Newtonian fluid, the hysteresis formed in shear stress versus shear rate curve is function of what? Duration of shearing? Yes, sir has told many times. Rate of increase or decrease of the shear rate. Kinematic history of the shear? Yes. Above, all above A, B, C points are correct. What I think is all above A, B, C points are correct. So D is correct answer. We will be actually looking at this one. So the concepts of hysteresis, that was the part of I think fourth lecture, the viscoelastic lecture. I can just see things are okay. Yes. So if you see this, then yes. Okay. Okay. Yes, this hysteresis I just yes, these are the hysteresis concepts, right? The time dependent one. So it was I think third. So sir has clearly explained this. So let us remind it again. These are some examples, graph related problems you should look at. Similar problem we will be solving this one. So here if you see this hysteresis. So hysteresis curves for thixotropic fluid and rheopactic fluid, you see. So this is in this way for increasing shear and then decreasing shear, but in this one the reverse is, this is clockwise, this is anti-clockwise, right? And then the reason for hysteresis is what? So the way this has been explained is, one is the history, right? And only one model that has been explained. This was the one, because it is very difficult to give the Hosca model was for this time dependent on field, and because lots of parameters come, so the number of parameters, you can see 8 parameters are coming up. So it is very difficult to handle if lots of realistic things you are incorporating within the equation, right? So this was it for this particular question. So this, if you see for this hysteresis, time independent hysteresis comes uh, for this non-Newtonian fluids, right? So and then if you actually want to take deeper insights of this, is see the behavior of thixotropic and rheopactic non-Newtonian fluids, and there if you see there the when you increase the shear rate, how the shear stress is behaving, and then whether there is this decrease of the viscosity, viscosity or increase of the viscosity. So the solution to this was so this this actually depends on all the factors, right? If I actually have to just give you answer to this, is the thing that we will be discussing right now. This one, you see that so if you see this, that the dependent non-Newtonian fluids such as things of idiopathic about which the hysteresis curves were there, the curves that sir has taught you in the class, let me just take that also here, because that actually helps you in exactly feeling the problem, right? Okay, so this was the curve that I am talking about. So this area under this curve, this hysteresis curve. So that is something important, as well as so this is hysteresis curve, right? Okay, so now if you see during this shearing, what is happening? Long shearing can lead to the structural breakup in thixotropic or build up in the retractive, right? So this alternate stress response is there. Then there's a fast ramp up or ramp down can lead to the larger hysteresis loop due to insufficient time for the fluid to restructure, right? And then this previous exposure to the shear exposure affects the current microstructure, and hence its current rheological response. So that is the one thing that was crucial in this particular regards to explain the concepts in line, right? Then the other question is the Deborah number. Very important if you are actually considering this for this particular thing, that is non-Newtonian freeze, and again in that this viscoelasticity, right? So Deborah number is the ratio between the deformation time to the relaxation, and then it is ratio between the relaxation time to the deformation time, the product of relaxation time and deformation time, and then the summation of deformation time and the relaxation time, right? So if you see this, then the main thing that you actually see is the relaxation time to the deformation time. So there was some numericals are solved in the class, and if you remember, in that numerical, it was very clearly explained, right? So let me just keep the explanation going. So this is the Deborah number that we are looking at, right? And then in detail we will be actually looking at this, what happens if it is high, what happens if it is low, that too we will be actually seeing. So it is a ratio between the relaxation time to the deformation time. So what is this relaxation time? It is time a material takes to relax stress after deformation. So again here the history is also important, right? So that's one thing that has to be taken. But this spring dog model and those things are included here. And deformation time or absorption time, what? Characteristic time scale of the process or flow, right? So let me just put it, give the detailed explanation of the same here. If you see, this is the Deborah number, and if Deborah number is high, then what is the condition in hand? Then high describe how solid like. If it is high, then the system is solid like, right? And if it is low, then the material behaves like a fluid, right? So the extent of solid like behavior or the elasticity is associated with the material is actually explain through this particular number, which is Deborah number. So it is relaxation time to the deformation type. Option B is correct answer, right? Is correct answer. So that is one thing. And then if you see the next problem that we are going to solve is on Ellis model. Okay, I think we have solved this question. That is shear stress tau half is what? So it is twofold. It is half of the infinite. It is half of the zero. So it is half of the zero. So this was repeated question. So no issues. So option A is correct answer. A is correct answer. Right. So let us put the solution of the same here. I think this was the solution, right? No issues. So let us solve the numerical problem that is here. I kept here at the last. You read it. I am giving you some time to actually feel the problem thoroughly, what it is saying. So both the problems are dependent with each other. So once you get comfortable with first one, then another one will be actually helping you to solve the first one. The next problem. So, and the third is this one, which is this one, right? So let's solve this one first, right? It will help. So consider the flow of this 10 weight percent, right? 10 weight percent. 10 weight percent of what? Aqueous polyacrylamide, right? Polyacrylamide, right? Solution. Having relaxation time of what? T relaxation is what? 100 milliseconds. The pack bed size is what? D is what? D micrometer. Okay, and the superficial velocity is what? 0.5 meter. What is the Deborah number? Okay, so T deformation, how you are going to calculate? It is nothing but D by Vs. Is 500 into 10 to the minus 6 divided by 0.5, right? So what it is coming is 1000. So it's 10 to the minus 3, right? Now Deborah number is what? Deborah number is Deborah number equals to TR divided by T deformation. So it is 100 ms divided by what? This was what? This was what? Meter per second. And this was what? So it is 10 it gave 1 millisecond, right? So 1 millisecond. So it's 100. So let's see what is the answer of this particular question. But at the same time, what I want you to see is this. Before just after this, we will be going to solve 17 and 18 question. That was very big in terms that lots of calculations are involved. Okay, so it's like 100, right? So it is correct answer. So regular number is correct. 100. So D option is correct. So is correct, right? So now this question that I was talking about is this. Look at this. Okay. So let's see. Yes. So this question is related to, I mean, the non-Newtonian models, Hartley-Berkeley model, and then we will be actually solving this. So for a carbopol solution, the shear stress versus shear rate curve can be approximated by both what? Both what? You see, it can be approximated by Bingham model and Herschel Berkeley, right? Then it is saying that this statement is valid only for the limited range of shear rate. Shear rate, limited range of shear rate means this is suppose shear rate versus shear stress, right? Shear rate versus shear stress, right? And it is for a given shear rate. Suppose for this range, these two models are valid, right? It is 0.1 to 200 seconds, right? The Bingham plastic viscosity is this. It is given mu Bingham is given. Bingham yield stress is also given. Tau Bingham. What is the value of n of Hartley-Berkeley model if Berkeley yield stress is 15? Okay, it is given tau Hartley is 15. It is asked that what is n. Okay, so how you are going to approach it? And in the next problem, what it is saying? Exactly same problem. Just it is saying that what is the m for Hartley, right? N and m value for Hartley. So you please solve this particular question. Okay, and then let's see what happens. Okay, so solve this. Meanwhile, I am joining, right? Okay, so if you remember that the model, let us just have a quick revision of the model and then we will be solving the question step by step, right? So the just the model, which is this Bingham and Hartley model. See, it was here in the second lecture itself. Very simply, it has been explained. So, so so this was after Alice. Okay. So Bingham and Hulkenberg. So these equations will be sufficient to solve the given question in hand, right? So that has been very well taught by sir in the class. So let's see. Cancel it, right? I want to continue it. Yes, so you see this. So in the Bingham, you see. So this was the one that been taught. So it is tau shear stress versus shear rate, and this is the this. So here the tau equals to tau b plus mu b times gamma, right? Right. And before, if you are less than that, there is no zero. So then there is this. You see, another one is this calculator, right? So these are a bit similar. Just this one you are replacing with this power, right? So significantly, m and n are same as in the power law model, and tau 0 h is calculated of the yield stress, right? So yield stress is when that changes. Okay, just tau b. Okay, so let's solve the question. And if you see that the values, the kind of values you are with, that is important to actually carefully look at the parameters given in here, right? So what I'm saying is, it's blank. So the blank slides we will be using. So for just have something dark that will be helping us a bit thicker. For Bingham, right, fluid. So first is Bingham fluid, that is BF. For that, from the sir's lecture, you know the expression is Yx equals to tau 0 b, okay, plus mu b minus dvx divided by py, right? Okay, so as per the given conditions, as you see the graph, here it is given tau versus gamma, and they are saying that for the 0.1 to 100, right? 0.1 to 100 or 200, let's see. To 200, right? What I'm saying, if you see this position, suppose this is the any curve is there, right? So for this particular point, if you see, what can be done is this one. For this 0.1, dvx divided by dy, which is gamma yx, this equals to 0.1. So this implies this tau yx equals to 20, which is given here stress plus 100 into 10 power minus 3 into 0.1 equals to 20.01 Pascal, right? And then for the another one, this was the gamma one lower. For the another one, what? Minus dvx by dy, this is 200, right? It is coming out tau yx equals to 20 plus 100 into 10 power minus 3, 200, right? It will give 40 Pascal. Okay, so from the this you got this shear stress values, right? Now you are having shear stress value. So now this curve, whatever curve was here, let me just copy that curve. I will just keep this curve. Yes. Now these values, this came out about 20. This came out about what? 40, right? So now this Herschel volatile fluid, what it says, tau ix equals to tau 0h plus m times minus dvx, which is gamma yx dy equals to power m. Okay, so from here if you see that we are going to, for this also, if you see this dvx, right, same thing you are doing for this Herschel-Barkal model. You are going to just equate those shear stresses to the model, and then this, and then another one is what? Minus dvx by dy equals to 2. It will give 40 equals to 50 plus m 200. Right? So now there is 2 equation and 2 unknowns. So when you solve these finally, so just take get the value of m. So from 1, so from 2, the value of m is what? 40 m equals to what? 40 minus 15 divided by 200 to the power 10. This will give 25 divided by 200 to the power 10. Okay, so this thing of, if you put in first, let us do it. So 20.01 plus 15, so 20.01 minus 15 equals to m 0.1 to the power n, right? 0.1 right? And this m is what? M is 25 divided by 200. So here 25 divided by 200 is a power n, 0.1 to the power n. So from here if you see this 5.01, right? You will come 1 by 5 equals to what? 0.1 divided by 200 to the power n. Right. So it is a 2000 to the power 1 upon 2000 to the power n. Right. So from here if you see, so solving you will be getting n equals to 0.2115. m equals 2 you will be getting. So here what has been asked, here you are asked about n, right? And only. So I think both questions we have solved, right? And m, the value of m will also come around 8 point something. 8.953. When you reverse put the value of n is 25 divided by 200 to the power n. No, so 0.2 and 0.2. This is correct. B is correct. Okay, and then what I'm saying is another one is this one. This one we have already solved, which is 8. C is correct. Okay. So just the solution of this, just paste it here. C. Okay. Okay, so this was it. Uh, this was it for today's class, which is transport phenomena of non-Newtonian fluid, week 1. Basic definitions of non-Newtonian fluid, and then basic models which are being used for the non-Newtonian fluid, especially this time dependent, time independent, and then this viscoelastic non-Newtonian fluids we have discussed today, and some examples related to week 0 and week 1 after this particular week. So we will meet in the next week where we are actually looking at some viscocapillarity things. So some instruments also we will be discussing, and then you please go through the lecture, revise it, go through this today's lecture. It will help you to solve the assignments, and then keep learning. This course is a bit I mean, it requires some prerequisites, some basic knowledge, so you can brush up that while attending the course. But definitely, it is very good research oriented course, right? So thank you so much. Thank you so much once again. So let me see if somebody is there. So, yes. So thank you so much. Overall, this transport phenomena. So even you are having very basic knowledge of transport phenomena, that will be getting brushed up, because here you are looking at some advanced concepts, right?